I'm Yvonne.
And I'm Steven.
Today we'll be exploring the chemistry of sunscreen. First, we will discuss the molecular basis of sunscreen protection.
And second, we'll do a little experiment on testing the effectiveness of different sun protection methods.
And thirdly, we'll discuss some environmental consequences of sunscreen. So why did we choose this topic? We're living in Singapore, a tropical country near the equator where we are being constantly exposed to high level of UV radiation from the sun.
So after doing a little bit of research, we found out that there are a lot of negative effects of UV radiation to our body, such as sunburns or even skin cancer, because the radiation can damage our DNA and skin cells and will cause uncontrolled cell growth and also skin aging. Talking about UV radiation, the first thing that comes in mind is always sunscreen. And on sunscreen, there's always a SPF label. So what is that? So basically, SPF is a measure of how much energy is required to produce sunburn under protected skin relative to unprotected skin. So this means that the higher SPF value is going to produce a higher protection to our skin and not being sunburned. So what is sunscreen's purpose? So it basically shields the skin from UV radiation. Also, the major thing that it can do is like it lowers the long-term risk to harm skin instead of just short-term sunburn. Sunscreen does not only show one type of UV radiation, instead it shows two types, which is UVA and UVB. UVA has the longest wavelength and it will penetrate into our skin, causing aging, wrinkles, and a lot of different damage to our skin, and it is protected by sunscreen. And for UVB, it's like the major cause that cause our skin to have cancer because it affects our outer layer of the skin. So it is like the most targeted UV radiation that the sunscreen is trying to protect. And the third type, which is UVC, but it's not including in this topic because it has a shorter wavelength and it is blocked by the ozone layer. So it's not even gonna reach our skin.
So let's talk about some photochemistry principles. So earlier from AP Chem, we know that light can behave as both waves and particles, and the energy of waves can be represented by hc over lambda, and this inverse relationship between energy and wavelengths means that UV light with shorter wavelengths carries more energy than other radiations with longer wavelengths like infrared radiation or microwaves. And specifically, UVB radiation with around 300 nanometers wavelength has enough energy to break chemical bonds, and this is what causes sunburn. So when the light hits a molecule on our skin or a molecule of the sunscreen, the energy from the light gets absorbed by the electrons in the molecule. So what happens after absorption? The energy has to be somehow dissipated, and there are four ways of doing this. The first way is internal conversion. This is the most ideal way of what we want to see in sunscreens. It happens when electrons are traveling from the excited state directly back to the ground state, releasing energy as heat. The second way is vibrational relaxation, and this only works for small amounts of energy because molecules are losing energy through vibration of the electrons within the same energy state. The third way is fluorescence, where energy is released as photons, and this is why some sunscreen will glow in darkness after being exposed to UV radiation. And the fourth way is phosphorescence, and this is undesirable for our skin cells because as the energy is slowly being released through light, it might lead to the formation of reactive oxygen species or trigger photo degradation. What makes a sunscreen a good sunscreen? To be effective, a sunscreen molecule must effectively absorb UV radiation from 280 nanometers to 400 nanometers, and it must be stable so it doesn't break down under sunlight, and it also should be non-toxic so it would be safe for human and the environment. When a molecule absorbs energy, it promotes electrons from the highest occupied molecular orbital to the lowest unoccupied molecular orbital, and the energy difference between the two orbitals is called the homolumo gap. If sunscreen molecules have a lower homolumo gap than the skin molecules, this will allow them to absorb UV radiation more easily, thus working as a sacrifice shield which absorbs the energy from UV radiation before it reaches the skin. So how do we lower the homolumo gap in sunscreens? A technique that is often utilized is called pi conjugation, which is an extended form of resonance. It involves alternating single and double bonds or lone pairs that allows the p orbitals to overlap, and this leads to the delocalization of electrons across the conjugated section of the molecule. This stabilizes the molecule and lowers the energy gap between the HOMO and the LUMO, and as a result, the sunscreen molecules can absorb UV radiation more easily before the energy reaches the skin molecules. So, in conclusion, sunscreen ingredients often utilize pi conjugation to lower the homo-alumo gap of the molecules, making it a sacrificial layer that absorbs and dissipates energy from the UV radiation before it reaches the skin molecules.
So we were just discussing about the underlying molecular mechanism of chemical sunscreen, and now I'm just gonna give a brief summary and also a comparison to physical protection from the UV radiation for the sake of our experiment. So physical protection is basically just like having protective clothing such as long sleeve shirt, long pants that has the ability to prevent UV radiation from reaching to skin molecules. And for chemical sunscreen, as mentioned, it's like a organic compound that undergo chemical reaction and that can convert the UV radiation energy to heat energy before damaging the skin.
After exploring the chemistry behind sunscreen, we conducted an experiment comparing the effectiveness of chemical and physical protection against UV radiation.
The aim of our experiment was to compare the effectiveness of chemical and physical protection against UV radiations. So we also included a control group with no protection layer. We applied the different protection layers onto the luminous beads, which absorbs and stores energy and dissipates it as photons, creating a glowing effect. Therefore, through measuring the brightness of the glow of the beads after being exposed to sunlight, we can compare the effectiveness of the different protection techniques.
So the independent variable of our experiment was the different protection methods. Firstly, we had a control group with no protection, and second, we had a group with chemical protection where we applied a sunscreen layer onto the beads, and lastly, we had a group with physical protection, which the beads were covered by tissue.
And these are some of our experiment photos. And for the green one, as you can see, there's nothing covering it. It's directly in contact with UV radiation. And for the blue one, it has a layer of sunscreen cover onto it as a chemical protection. And for the pink one, it's covered with a piece of tissue, which is a physical protection. And these are the results for the experiment. And as you can see, the green is the brightest, followed by blue and red. So the brightness of the bead represents the amount of energy that UV radiation is absorbed by the beads, meaning that it is not being pre-absorbed by the protective layer. The brighter the glow is, the less effective the protection was, and it is because more energy is absorbed by the beads instead of the protection layer. So in conclusion, physical protection is more effective than chemical protection and no protection.
So now let's talk about the environmental consequences. The amphiphilic nature of sunscreen molecules, meaning that it has both polar and nonpolar regions, is essential for its function. The nonpolar regions are essential because it allows uniform adhesive spread of sunscreen on the skin by adhering to the skin's nonpolar lipids. It also allows the sunscreen to dissolve well in nonpolar emulsions, for example, oil droplets. The polar regions are also essential because it allows the sunscreen to be washed off, and it ensures the sunscreen stays only on the surface and doesn't penetrate the skin too deeply, and it also ensures that the sunscreen dissolves well in nonpolar emulsions like water droplets.
So what will happen when sunscreen enter to the ocean? So basically, the polar regions of the amphiphilic molecules will allow sunscreen to be easily washed off from the skin by the ocean water. But the nonpolar region will prevent the molecules from completely breaking down and will keeping them persistent in water. And this will eventually lead to bioaccumulation, which means the building up of chemicals in organisms over time, and coral bleaching, which is created when the amphiphilic molecules pass through the hydrophobic lipid membrane and the hydrophilic cytoplasm. And this will reach the sensitive organelles such as DNA or mitochondria in corals.
And this is why recent scientists have been trying to create environmentally friendly sunscreen that are non-toxic to our environment.
Thank you.